Hello, this is Jack Jackson. In this video, we're going to talk about an amazing discovery that was made in the 19th century, and that is of non-Euclidean geometry. The 19th century saw this discovery or creation of non-Euclidean geometry. A new non-Euclidean geometry we now call hyperbolic geometry was discovered, which has all the same postulates as Euclidean geometry, except that it violates the parallel postulate. After this remarkable shocking discovery, sets of postulates and axioms were no longer thought of as being a list of things that describe the physical world or as the only possible postulates. Instead, they became a list of rules of the game for a particular system which may or may not adequately describe the world. This was a transformative development not just in geometry, but in all of mathematics. This actually changed the way we could look at mathematics and helped spur on some of the further directions that mathematics would go in the 20th century. This work came to fruition with the works of Luchesi, Boli, and Gaus in the 19th century, but it was developed in an attempt to prove Euclid's fifth postulate. Earlier attempts to prove this postulate go back almost to the time of Euclid himself. In the elements, Euclid had 5 postulates. Number 1, a unique straight line segment can be drawn joining any 2 points. 2, a straight line segment can be extended indefinitely in a straight line. 3, any straight line segment, given that a circle can be drawn having the same segment as radius and one endpoint as center. Number 4, all right angles are congruent. And number 5, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. Well, do you see one of these things is not really kind of like the others? Well, that fifth one seems to be much more complicated than the rest. And for over 2,000 years, many very good mathematicians tried to prove it from the other postulates, thinking it should be a theorem. Some even thought they had succeeded, but always there was some additional unstated postulate that was being assumed. The Euclidean parallel postulate is equivalent to, given any line L at a point P not on L, there exists exactly one line through P parallel to L. This form is now known as the Playfair version, named from John Playfair's commentary on Euclid in 1795, but this version had been known at least as far back as Proclus in the 5th century. Now, many mathematicians have worked on this. Here's a partial list of some prominent mathematicians that all made attempts at proving Euclid's fifth postulate, and all failed. Of course, we now know they were all doomed to failure since it's impossible. The fifth postulate is actually independent of the others, which in a way vindicates Euclid for including it as a postulate. They all ultimately assumed some postulate that was equivalent. Claudius Ptolemy worked on this as early as the 1st or early 2nd century. Dionysius Proclus criticized Ptolemy's quote proof and made his own proof, which was actually also incorrect. He was around the 5th century. Ibn al-Haytham in the 900s or early 1000s attempted a proof by contradictions, and he introduced something we now call Lambert quadrilateral. Omar Khayyam from 1050 to 1123 is his dates of his life. He attempted a proof. Nasir al-Din al-Tusi in the 13th century critiqued earlier attempts and made his own attempt at a proof. Girolamo Vitale in the 17th century made another attempt. And Legendre, who in the 18th century, early 19th century, spent 40 years working on and off on the parallel postulate. And 2 people that I want to lift up came very close to discovering Euclidean geometry, non-Euclidean geometry. Okay, that is Johann Lambert, and he in 1766 he made a further attempt. He used a Lambert quadrilateral with 3 right angles and tried to prove the remaining angle had to be a right angle. He was able to show it was not obtuse, but failed to show it cannot be acute. He came pretty close to discovering hyperbolic geometry. And just before that, Girolamo Sacchieri came very close to discovering hyperbolic geometry without actually doing so. He used a Sacchieri quadrilateral It's a right trapezoid with congruent bases, and he knew that there were two right angles, and he proved the other two angles were congruent and non-obtuse, and he was trying to prove that they had to be right angles. And he was able to prove many results in neutral geometry, but at the end, he just could not make that intellectual leap to think there might be a geometry different than Euclid's geometry. So some of the first people that worked and actually came up with non-Euclidean geometry, really probably the first one who actually came up with it without publishing it was Carl Gauss. He lived from 1777 to 1855, and when he was at school, he was friends with Felix Boli, who was about the same age. He lived from 1775 to 1856. They were students together at Göttingen, and they worked together on trying to prove Euclid's fifth postulate. This became kind of an obsession of Felix Boli, and he was mainly focused on the foundations of geometry and the parallel postulate in particular. And he wanted all the postulates to be independent and obviously true. In 1804, he thought he had a proof of the fifth postulate, but Gauss found his error. He finally gave up and decided to find another equivalent postulate that was more acceptable as obviously true by common sense. Farkas encouraged his son Janos Boli, who was born in 1802 and lived till 1860 in Hungary, well now it's in Romania, to study mathematics, and he was his first teacher. And he strongly encouraged him not to work on the parallel postulate. Fortunately, he didn't heed his father's wishes on this item, because Janos was one who came up with hyperbolic geometry and non-Euclidean geometry. Janos learned calculus from his father by the age of 13, by which time he was in college. Farkas asked Gauss to let Janos live and study with him, and Gauss declined. Janos ended up attending a military academy of engineering at Vienna, graduating at 20 years old. And he spent 11 years in military service as an engineer. He spoke 9 languages. In 1820, at 18 years old, he started studying Euclid's fifth postulate, and even though his father had told him to give up on it. In 1823 to 1824, he discovered hyperbolic geometry, a geometry that is consistent with all the postulates of Euclidean geometry except for the parallel postulate, complete with multiple theorems. He published it in 1831. He sent a copy to Gauss. Gauss's response was interesting. He wrote to a friend saying, "I regard this young geometer, Boli, as a genius of the first order." But he wrote to Boli's father, Farkas, to say, "To praise it would be to amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which has occupied my mind for the past 30 or 35 years." Now, if it had been somebody else besides Gauss, you might say, well, he's making this up, but it's probably true. In November 1824, Gauss wrote in a letter, "The assumption that the sum of the three angles of a triangle is less than 180 degrees leads to a curious geometry," hyperbolic geometry, "quite different from ours, Euclidean geometry, but thoroughly consistent, which I have developed to my entire satisfaction, so that I can solve every problem in it except the determination of a constant, which cannot be fixed a priori. The three angles of a triangle become as small as one wishes, if only the sides are taken large enough. Yet the area of the triangle can never exceed or even attain a certain limit, regardless of how great the sides are." Gauss never published his work on non-Euclidean geometry, fearing that the world was not ready for it. He did not like controversy. Boli found that Luchesi had published the discovery of hyperbolic geometry in 1829, 2 years before Boli, and Boli felt that Luchesi had plagiarized his work, or perhaps Gauss had told him about it. So how about Nikolai Luchesi? He's actually the first one to publish results on non-Euclidean geometry. He was born in 1792 and lived to 1856 in Russia. In 1807, he studied at Kazan State University. One of his professors was Martin Bartels, who was a friend of Gauss's, and they corresponded. And he graduated in 1811, and by 1814 was known as an excellent teacher at the university. He worked on mechanics, hydrodynamics, integration, differential equations, calculus of variations, and mathematical physics. In 1823, he published his work on non-Euclidean geometry, making him the first to ever publish non-Euclidean geometry, what we now know as hyperbolic geometry. His treatment was fully worked out and was very similar to that published 2 years later by Janos Boli. So, who should deserve credit for it? Well, really, mathematics historians now believe that Gaus, Boli, and Luchesi all independently made the same discoveries about hyperbolic geometry, even though it would have been possible for Gauss to have given either Boli or Luchesi hints, since he made his discoveries first and was in correspondence with people close to both Boli and Luchesi. But given Gauss's reluctance to publish, it seems unlikely that he did that. If we follow the story forward just a little bit, Bernard Riemann, who lived from 1826 to 1866 in Germany, had something to do with furthering the study of non-Euclidean geometries. In 1854, he gave a series of lectures that were published in 1868, 2 years after he died, reimagining geometry as a space with a metric for measuring distance. He gave a treatment of what we now call spherical geometry or elliptical geometry, where no parallel lines are possible. Eugenio Beltrami, who lived from 1835 to 1900, also did some work with hyperbolic geometry. In 1868, he gave an essay on the interpretation of non-Euclidean geometry, and in that he produced a model for 2D hyperbolic geometry within 3D Euclidean space on the surface of a pseudosphere, which you can see pictured right here in this colored picture to the right. And it's found by taking this tracix, this blue curve here, and revolving it around its asymptote. So he was able to give a physical model now for hyperbolic geometry, and now that kind of made it seem more legitimate. Felix Klein was also a fantastic geometer. He lived from 1848 to 1925, and he came up with his Erlanger program, which viewed geometry as a study of the properties of a space that are invariant under a group of given group of transformations. And he made connections between group theory and geometry, and he revolutionized the way we think about geometry. And he showed that the three types of geometry are all on equal footing: spherical or elliptical geometry, where no parallels are possible; Euclidean geometry, where there's exactly one parallel to a given line through a given point on a line; hyperbolic geometry, where there are infinitely many lines parallel to a given line through a point on a line. We might also mention he's famous for creating his Klein bottle, which is a one-sided three-dimensional surface. It's kind of like one layer level up from a Mobius strip. And finally, I want to mention Henri Poincaré. He lived from 1854 to 1912 in France. He was the originator of algebraic topology, the originator of analytic functions of several complex variables, and he did a lot of work on algebraic geometry. And worked actually in several areas of applied mathematics as well. He came up with the disk and half-plane models for hyperbolic geometry. I typically use the hyperbolic half-plane model, sometimes called the Beltrami-Poincaré model, whenever I do my study of hyperbolic geometry with college students. And so you can look at my geometry lectures videos, and you'll see quite a bit of hyperbolic geometry developed using Poincaré's half-plane model. So this was a fantastic discovery that people didn't see coming, and it really changed the way we looked at geometry, the way we looked at mathematics, the way we looked at the world.